What we're going to do in class, the labs are out here, guys, is we're going to do the lab on the common collector amplifier. And this is a handout lab because for some reason, they took this amplifier out of the lab book. They took a couple of really good labs out of the lab book, and one of them was the common collector amplifier. So we're going to go through the lab and look at it. So I have the circuit set up here, which you see, it's got some really good information. So you probably need to go ahead and get your formula sheet out. And we need to go ahead and solve for the circuit in procedure step 4. So what we're going to do is compute the values. We're not going to put 1 volt peak to peak in there because we know that our function generator can't put out 1 volt peak to peak. But this guy, remember the voltage gain on it. What's the voltage gain on the common collector amplifier? Yeah, it's about 1. In fact, it's slightly less than 1. Yeah, so we're powering up on 10 volts. If we bias this thing correctly, pretty close to the center, we could put almost a 10 volt peak to peak in there. So what we'll do on where it says 1 volt peak to peak, we're going to put, I don't know, we'll put something that makes it easy to measure on the oscilloscope. So right now I'm putting in, let's go ahead and do it. So let's see, right now, step 4. Yeah, there should be a circuit in step 4. The book gives a lot of, the lab book gets some formulas that get very, very complicated. If you look at, step 4, this shows you how to calculate Rn. That's a lot harder than what we need. Then if you look at formula 3, this shows you how to calculate AB. And we don't need to calculate AB because we know it's going to be slightly less than 1, right? You understand? The input resistance we've already looked at. That is the formula that we use. By the way, when they use those pipettes, those 2 lines in parallel, it means that would say R1 in parallel with R2 in parallel with. Of course, we know we can't use that as a formula. We have to use the reciprocal of the sums of the reciprocals, right? So what we need to do is get out our formula sheet, and we'll go ahead and calculate some of this stuff. So we're going to put in probably, let's say I got it on 500 millivolts per division. We'll just go ahead and put in 2 volts to the thing, because I know we can get 2 volts. I think we get 2 volts. No, we can't get 2 volts. So let's go ahead and put 3 volts in. I'll go and adjust that. So 3 volts in, we should get about 3 volts out, right? But it's going to be slightly less because, anybody know? This is common collector. Y'all, the common emitter lab, y'all still going to work on? So our circuit, this guy here, in my opinion, is a lot easier to calculate. So it's a voltage divider bias. So here they're calling R1, and it's a 33K. Here they're calling R2. This is a 39K. By the way, you notice that this has been changed. I'm actually changed. The way they had it biased in the book was awful. Then we come over here, and then we have our transistor. VCC is connected directly to the collector because this is a common collector. And then we have an output resistor of 1K. And then we have an output capacitor, or a coupling, not a coupling capacitor. And then we have, oops, missed my center, but that's okay. And then we're going to put our signal generator right here. We're putting in 3 volts peak to peak. Why? Because our signal generator won't even put out 2 volts. And then VCC is equal to plus 10 volts. Okay, guys, what's the first thing we need to calculate? VB. Okay. So what's VB going to be equal to? Good, 39K. Oh, 72K, right? It's over the sum. 39K over 72. Notice I left the K out. Why I leave the K out? Yeah, it's going to cancel out. And then we'll multiply that times 10, and that should give us our base voltage. Perfect would be 5.7 volts, but it's going to be impossible to get. But we do pretty good. 5.42 volts. We okay? Then we would collect. We would calculate our emitter voltage. So V on the emitter is going to be 5.42 volts minus 0.7, right? So what's our emitter voltage? What's that? Okay. What else does it want us to calculate? IE. So IE would be equal to 1K, 4.7 divided by 1K, which would be 4.7 milliamps. I like that. Are we okay? VB, VE, IE, voltage collector to emitter. Voltage collector to emitter is going to equal to what? What's the voltage on the collector? 10 volts minus the voltage on the emitter, 4.7 volts. Oops, it should equal what? Yeah, I'm sorry. Okay. Now what we need to do is move down into table 39. (39-3). RVB, by the way, we need to mark that out. We're using what? 3 volts peak to peak. So what should VE be? By the way, normally when they use lowercase letters like this, they're indicating AC parameters. When they use uppercase letters, it's what? DC on the subscripts. So what would VE be, guys? What would VE be, guys? What's the voltage gain on this guy? Huh? About 1. So if I took 3 volts peak to peak in and multiplied it by 1, what's that going to give me? 3 volts peak to peak out, yeah. So that should be easy. Of course, we know it's going to measure a little less because of RE prime is a resistor there, and it's going to drop some voltage. But that's going to be the difference. It's going to be the difference between what the base current drops on RE prime. Right? You'll understand that. That's the only difference between our input. RE prime, we need to calculate that. What's the formula for RE prime? For guesstimation on RE prime. They're calling it RE, by the way. We called it RE prime. Not milliamps. Yeah, but we don't need to put volts. We don't need it. Over what? IE. IE is 4.7 milli. Millis are going to cancel. So it's going to be a little over 5, right? What is it? 5.3 ohms. So if I knew the base current, then I could calculate the voltage drop of RE prime. It's not going to be much, is it? Because base current is really, really small. So ours should be really close. I need to calculate AV. Well, we don't need to calculate that. It's approximately what? 1. I need to calculate RN, which I call ZN a lot. So here we come in. Here's our AC coming in. What does it do when it gets here? Splits up and splits down, right? Comes flying over here. Don't go up through the collector because it's reverse bias. Comes through here. Now we're dealing with beta. Hits this point right here and goes that way right there. So, what's typical beta on 3904? We've been using it a lot. Typical beta is 100. Remember, that's a guesstimation, right? But it's worked out pretty good for us. I think when y'all did y'all's common emitters, some of y'all had calculated a gain of like 80, and some of y'all measured 70. I think the gain calculated was 90, and some of y'all measured 80. You have to use RE prime for that. So here we go. So first of all, let's go ahead and do this guy. So this is called RE, and this is they're calling this R load, right? Well, they're not called anything, but yeah, they are. So let's calculate that. So RE in parallel with R the load is going to be 1K in parallel with 1K. They're the same size, 500 ohms, right? Everybody okay? Okay. So now we're doing the same thing that we just did for the common emitter. Let me go back to black because I used everybody okay? Lost anybody yet? Everybody okay? Yeah, in parallel circuits, if you got two resistors that are the same size, or if you got multiple resistors that are the same size, you can take one of the resistors and divide it by the number of resistors, right? But they got to be what? They got to be the same size. Okay, so Rn or Zn, whichever one you called it, is going to be 1 over 33K plus 1 over 39K plus, we're going to ignore RE prime. Why are we going to ignore RE prime? Because it's so dang small, right? You understand? So this is going to be 1 over, this guy here is not bypassed, so we're going to say 1 over RE is 1K, I'm sorry, R out, so this is 500 ohms, times beta, and what are we using? So you need to do this guy first, work this backwards, right? So it'd be 5 times 100. What's 5 times 100? What's that? 5 times 100. Oh, 15.2K input. RN? 15.2K? 13. Sorry. Everybody okay there? Everybody get the same thing? So real high input impedance, real low output impedance, which is what one of the characteristics. 2K, 13.2K ohms. So that means my AC input signal is going to supply enough current to support 13.2K, my output is looking at, my output impedance is 1K, but Z out is 500 ohms, right? So guys, I think we got everything. What do we need? Oh, power gain. Let's do power gain. So the power gain can equal, we know power is equal, we know the power is equal to V times I. Of course, this guy here in power gain, so AP would be equal to AV times AI. That makes sense? But this guy right here is 1. So I mean, basically, if we can figure the current gain, calculate our current gain, then we can calculate the power gain. And this is not measured, this is computed. Okay, guys, so how are we gonna figure this out? I think isn't it in your formula sheet? AI, common collector. So on your formula sheet, you should have a bunch of formulas for common collector. And one of them over there should be for AI. And it's pretty neat the way they came up with it. So, did we show you how they came up with that? Where we say, so AI would be equal to IN. So how would we calculate IN? We'd calculate IN by doing what? By taking VN and divided it by RN. And that would be my input current, right? Then we would multiply that times VN, V out, I'm sorry, I got this wrong. Duh, I'm saying, man, you're doing something wrong here. Power gain is not I got the power formulas in my mind, but we're trying to do gain. So this is going to be calculated, so this would be V out over R out. Y'all understand that? So what's this the formula for? This is the formula for our input current, right? You understand? This is our formula for our output current. And I got that backwards, right? Somebody say you got that backwards, Rich? What's the formula for gain? Any gain. I over N. So this would be V out over R out. That would give me I out, right? You understand? Yes or no? Divided by Vn over Rn or Zn. That would give me my input current. How do we divide fractions? Invert this guy over here and multiply. So that means I could come over here and I could say V out over R out times, right? Understand? It would be what? Rn over Vn. So I'm going to combine these right here. Well, these two things right here are what? V out and Vn are what? Somebody say the what? Same. So that means they cancel each other out. So that means we can calculate the current gain by using Zn over Z out. You understand that? Which is pretty cool, right? So my Zn is what? 13.2K. My Z out is 500 ohms. So what kind of current gain we're going to get out of this puppy? Pretty good, ain't it? What's that? I can't hear you. 26.4. What unit is that? Okay, so that means AP, we should expect an AP of 26.4. Y'all understand? So there we go. So that's got everything we're supposed to compute, right? Everybody okay? Everybody okay? So we're ready to do our what? We're ready to do our measurements. Try to bring the meter into play. So here's the meter. Let me change the angle of the dangle. Get it so it don't reflect. Need to change it back just a hair. Okay, so everybody can see the meter. I got my meter set on DC, 40 volts, because we're expecting 5 volts, right? So what's the first thing we're supposed to measure? Up at the top. So we're back up in table 39.2. So we need to measure VB. We're expecting what? 5.4. Okay, so here's our measurement. 4.8. Not too bad. 600 millivolts different. Okay, what's the next thing I need to measure? DE. We were expecting what? Okay, so here we go. We know it's going to be less now. So here we go. 4.11. We're not going to measure IE. We'd have to break the circuit. But we've calculated, right? Everybody okay? Yes or no? Going to come up here and measure voltage collector to emitter. That's next, right? So here's my collector. Here's my emitter. 5.86 volts. Yeah, because we didn't get the right base. Our base is a little low. If the base is a little low, the transistor's not turning on as much as we calculated. If the transistor's not cutting on as much, it's going to drop more voltage. So VE was lower than what we calculated too. But the sum of VE and this should still equal 10 volts, right? Let me go back and double check that, by the way. Oh, sorry. I hadn't touched it, but you know these power supplies. So we got 9.97 volts. That's pretty dang good. Okay, so next one we're going to measure, have to measure with our oscilloscope. So we've got our oscilloscope set on. Get the measurements. Can y'all see it? Well, that focused in pretty good, right? 500 millivolts per division. So 500 millivolts per division. There's 1, 2, 3, 4, 5 divisions. So that's 2.5 volts. I need 3 volts. So let's go ahead and raise it up. So that way we won't have to change anything. So 1, 2, 3, 4, 5, 6 divisions. So that's 3 volts, peak, right? The one right below that, this is my output. Let me turn off the, and I'm going to raise it up. And we're going to put them on top of each other. And y'all can't see it, but there's a little space right here. So what do we get out? They're right on top of each other. So 3 volts peak in. What do we get now? 3.3 volts. Measured AV, what's our measured AV? 3.3, 3 volts peak in, 3 volts peak to peak out. Out over in is going to give us a gain of about what? What's the gain going to be? 1? Yeah, good. So everybody okay so far? Any questions? Okay, so what we need to do now is measure RN. RN's a little harder to measure. Anybody remember how we do that? So we got a pot, 10K pot. Now we're going to turn power off. And we're going to come over here and put this in series with our input. So where's my input at? There's my input. And we're going to wire it up to be a rheostat, right? Okay. And what are we going to do? Somebody tell me. So what I've done, I didn't put it in the exact same spot, but it's going to have the same results. What I've done is I've come over here and I've got a pot wired as a rheostat, and I put it right here. And now my signal's right there. So when I put the scope back up here, I have my pot set to 0. So notice, oops. So I've got my pot set, I got my rheostat set to 0, and it's still, I'm losing something, guys. I'll see what's going on. Okay. And when I start adjusting it, let's see if we can do it. Because, okay, so what am I shooting for? Half. Because if it halves, that means the input resistance of the amplifier has to match the resistance of the pot, right? So we got 3 volts, so we're going to try to get it down to about 1.5 volts. And we're going to be, I might have to get a bigger pot. Why? I got a 10K pot. And what's the problem? We'll try it. We calculate our input impedance to be 13.2K. So if it's 13.2K, I won't be able to do it with a 10K pot. But I'll have to get I can get a resistor, right? And put it in series. But we'll see if we can get it. So here it comes, it's starting to drop down, This is the best I could do right there. So we're putting 3 volts in, so I need 1.5 volts out. Which would be 3 divisions, so we can't do that. So 1, 2, 3. So it's pretty close to 13K. Y'all understand? Yes or no? Okay, so what I'm going to do is I'm going to grab a resistor, another resistor real fast. Let's try to anyway. I don't know if I've got one big enough in here. Here's a it's gonna be too big. Here's a blue, gray, red. What's that? Come on. Blue, gray, red. Blue, gray, red. Blue, gray, red. $6.8K. Of course, when you know we lost it completely. So let's see what else I did when I was moving around. Oh, I turned the power supplies off there. So we're shooting for 3 divisions. One, two, three. That looks pretty good, right? Okay, now what we need to do, we need to turn it off and measure our total resistance. Okay. So I'm going to turn this off, swing it back over to my meter, put my meter, okay. I'm going to have to disconnect it from my source. I'm putting one lead on this side of the 6.8K. I'm taking my other emitter lead and putting it on the other side. I have it on K, 40K. That's not good, guys. It's okay now. It was measuring about 15K when I touched the 2 leads together. So when I came up and touched the 2 leads together. So I have my, here's 6.8K, here's my pot, here's my other side. I'm going to touch this. So what was happening is it measured over 30K, and when I touched it over to my other side, it wasn't going to 0. And so if you got a dial meter and it's doing something strange, you need to, you know. So now it looks okay. So we're going to go up here, put it back up on our meter, and it's measuring 15.5K. Not too bad, right? We calculated 13.2, measuring 15.5. So now we can calculate our gain. So our gain is going to be a little higher than what it was, because we were using 13.2K to calculate our gain. Here we actually got we measured 15.5, right, or 15.46. So now we can take 15.46 and divide it by 500, and that should be our power gain. So we got a pretty good power gain out of the thing. What was our power gain now? Yeah, so we actually these are measured values, right? I got a power gain of 31. And so what's the advantage with common collector? We have a high input impedance, right? And we have a low output impedance. We don't get any voltage gain, but we get a lot of current gain. And these guys are used to drive a lot of high current loads. So like speakers. Speakers are looking for current because they generate magnetic fields, right? You understand? They have a very low impedance. We couldn't drive that sucker with a common collector. A common collector's got a moderate to a high output impedance, right? This guy's got a low output impedance. We can drive speakers, any solenoids. We can drive motors with them, right? You understand that? But we'd have to get our voltage gain out of the way before we got to the common collector. So what we'd probably do is we'd use common emitters to get a real good voltage gain, right? You understand? And then and it's got a high output impedance, feeding it to the high input impedance of the common collector, low output impedance, and we can get a really good current. We can get a real good current gain out of this. So these are the two predominant out there. It's common emitters. They're probably the most widely used because they get both power, voltage, and current gain, right? So they have a high power gain. But when we say a high power gain, we're still talking about milliwatts, right? You understand that? And then when we need that real high current, who gets the job for real high current gains? Common collectors. Common bases are used a lot in extremely high frequency, but you got to give those guys a lot of power because they have no current gain at all. They have a real good voltage gain, but they have no current gain at all. In fact, their output current is a little less than the input current. And why is that? Because we input on the emitter, and the emitter carries how many currents? 2 currents. So all the emitter current does not get to the collector, which is where the load's at. You have to take the base current out. So common bases have a current gain of less than 1. So what we're going to do now, we're going to break this thing, right? But before we break it, let's try to anticipate what's going to happen if I open R1. So what we're fixing to do, we're fixing to put some problems in this thing. So the first problem I see is we're going to open R1. It's asking for DC predictions. So what do you think is going to happen to VB if we open R1? So what? Well, here's my voltage, here's my common, right? You understand? We're opening R1. Where does that 5.41 volts come from? It don't come from common. It comes from what? Okay, so what should we expect VB to do? It's gonna go to 0, right? We'll have a little leakage current back through this guy right here, but it's going to be very, very low. We might measure in the millivolts there because we have that leakage current. This guy here is still reverse biased, right? You understand? Okay, so what's going to happen to VE? Well, what sets VE? VB. How much VB do we have? 0. Okay, so we expect that to go down a lot, right? Okay. What's going to happen to voltage collector to emitter? So what is the transistor? Is the transistor on or is it off? Huh? How much base current how much base voltage do we have? Okay, how much base current do we have? Okay, what does this guy do? I mean, it's a current valve. We use a current to control the current. We have no control current. So what's it going to do? Is it going to cut off or is it going to cut on? No base current, guys. What's it going to do? It's going to cut off. So what should we measure across here? It's an open element in a series circuit. What should the voltage collector emitter go to? 10 volts. Okay, so that's what we anticipate, right? So let's see. So we're going to come up for an open R1, which is the what? 33K, right? So all I'm doing is going to come up and disconnect it. And this is troubleshooting. This is really good because what do resistors do? Well, resistors open a lot. So here's the 33K right here. So we're going to come up here and open it. Make sure we still got VCC. Okay. So I've opened R1. I'll turn the power supply back on. Put my meter back on volts. And what's the first thing we need to measure? Okay, VB. So here's VB. Of course, that's that little bit of leakage current coming back to the collector, right? Okay. Here's VE. About 190 millivolts. Just leaking through the transistor, right? Voltage collector to emitter. Let me move it over here. So here's my collector. What do you expect? Expect 10 volts. Oh, that's my base. Sorry. I'm trying to figure out where I can get on the collector at. Oh, I can get on it. No, I can't get on it there. I can get on it back here at the power supply. To emitter, 9.98 volts, that's what we got applied to it. So, okay, that's what we anticipate. So if you can anticipate what's going to happen, then you're troubleshooting, right? Okay, what are we going to do now? I'm going to put R1 back. What's the next thing we're going to do? R2. Okay. So we're going to open this guy down here. What do y'all think is going to happen? So is the transistor going to cut off? Is there still a path for current to get through the base? So the transistor is going to cut on. This 5.4 volts was set by that resistor right there. That resistor is open. Should we expect the voltage to go up or go down? Got to anticipate, guys. What do we expect? It's either going to go up or it's going to go down. Okay. You think it's going to go up? Who thinks it's going to go up? Guys, this guy over here is looking at, this guy over here looks like a, what does it look like? A big resistor. So this is what's happening. So I've got this guy right here. Okay. Then I come over here, and then I've got this real big resistor over here. What was the size of that? This is 39K. What did it see this over here? Is that 50K? This resistor right here. We're talking about DC bias. We're not talking about AC. It sees this guy as times beta. The beta is 100, so it sees this as 100K. Okay, understand. Which one is setting the voltage? Well, this guy right here is setting the voltage. We got less than a 10. I've opened this guy up right here. Now that 100K is setting that voltage. So what's going to happen? It's going to drop. Is it going to drop less? Does 100K drop less voltage or more voltage than a 39K? It drops more. So that's going to cause this voltage right here to do what? Go up. If the base voltage goes up, what happens to the emitter current? It goes up. What happens to the transistor? It moves toward saturation. It's going to saturate. I mean, it's going to saturate hard, right? You understand that? So let's see if we anticipate that. So we should expect this voltage to go up, right? You understand? Got no AC signal. This is bias, by the way. So we're not paying attention to this resistor over here. This guy right here has nothing to do with IE. This is AC. So the AC goes this way. The DC bias goes there. We've opened up this resistor. This guy is seen as times beta. Typical beta for this, and it turned out to be pretty good, is around 100, right? We used 100 and came up with 13.9K as our input impedance. We measured 15K, so 100s are really good for this transistor right here. This guy goes up to 100K, causes this voltage drop to go up. It's going to cause that voltage drop to go up because it can only be 0.7 of a volt. Just say this guy's going to saturate. So voltage collector to emitter, we should expect it to do what? Is it going to go up or go down? Huh? Saturated transistor. What voltage do we use to determine if a transistor is saturated? Voltage collector to emitter. If we say if it's less than a volt, we consider it to be what? Saturated, right? If it's equal to VCC, it is cut off. If it's in between that, we consider it to be in the active region. We ought to put a scope on this and let y'all see this. Man, it's going to be really saturated. Come up here, look at my, get my meter out. Going to take my common and connect it to circuit common. Okay, where's my other meter lead? Here's my base voltage. Here's VB. Got it turned on. Let me open the resistor first. Here's VB. Can y'all see? Oh, Rich. Supposed to measure what? 5.4 volts. Measuring 8 volts, which is what we expected. We expected it to go way up, right? We could have pretty close to calculated it. So if the base voltage goes up, the emitter voltage goes up, means the voltage drop across that. So here's my emitter voltage right now. We should expect it to be 0.7 of a volt higher, so it's 0.7 of a volt. My voltage collector to emitter. So here's my emitter. Here's my collector. Measuring 2.6 volts. Still not quite saturated, but it's close, right? So when we do predictions, let's don't try to come up with the actual value. What we need to do is determine if it's going to go what? Up or down. Okay, guys, you'll take a 2-minute break. On short R1. So I'm just going to come up here and place a jumper around it. By the way, very seldom see a resistor short, but we do see them shorted when people make mistakes. So people soldering, a lot of times when people are soldering, they drop solder on their circuit card, or when they clip the leads too long, and then when they press them down, they bend out and short against other things. Normally resistors will open or the resistance value goes up. So I'm going to come over here and just place a short. But let's go ahead and anticipate. So what do we anticipate is going to happen? So yeah, VB is going to go way up, right? Because we're connected directly. We're connecting it directly to VCC, so it's got no option to go up. In fact, it's going to go up 10 volts. VE is going to go real high. VE controls IE. IE is going to go up. IE goes up. Transistor moves towards saturation. So this guy will saturate transistor. Probably go pretty close. The voltage collector to emitter is going to go way down, right? So we'll go ahead and measure voltage collector to emitter. I have it ready right now. Let me bring my camera back up. So we'll measure that first. So here's voltage collector to emitter. Let me make sure we're measuring something, because it's definitely saturated. Okay, so what am I doing, Rich? Let's go right here. Okay. Still got 10 volts. Okay, so let's switch over. So I'm measuring what? Base voltage. Here's base voltage. Here's VB. Oh, my short came up. So which one we shorting out? Which is which one?
33K.
What's that?
33K.
33K. Okay, so this should short it out right here. Okay. So here's my base voltage. Yeah, which is what we have, or 10 volts, right? This is what we have here, which we would expect. What's going to happen to my emitter voltage? Here's my emitter voltage, 9.25, which is about 7/10, is what we expected, right? What's going to happen to my voltage collector to emitter? It's going to drop down pretty close to 0. So here's my collector. Here's my emitter. It's measuring 730 millivolts. 727 millivolts. So what's that? Less than a volt. This guy's saturated. And that's what we expected, right? So that's R1 shorted. Take the short back out. Here's there. So we're back to normal. What are we going to do now? RE is going to be a little hard to figure out. So what do we think is going to happen? So I got the short removed. And we're going to come up here and we're going to open RE. What should happen to VB? Is it going to go up? Is it going to go down or remain the same? It'll be pretty close to the same, right? Because we've been ignoring this resistor over here anyway. What's going to happen to voltage on the emitter? Is it going to go up or is it going to go down? What do we anticipate? Is it going to go up or is it going to go down? You're either right or wrong, guys. I mean, it's a 50-50 chance. It's not going to remain the same because there's no current flowing through it anymore. Right? You understand? So that 0.7 of a volt should be non-existent. There's no bias. There's no base current flowing through the emitter. So who says it's going to go up? Huh? PE. That's what we're looking at. That's what we're at. We're trying to anticipate what's going to happen when RE opens. So who thinks it'll go up? It's either going to be right or wrong, right? It's either going to be right or wrong. It's no big deal. This one's kind of strange because the 0.7 of a volt's not there. RE prime's not there because RE prime is set by what? RE prime is set by IE. There's no IE because there's no VE, right? Or something. We're going to measure something there. I think it's probably going to go down. This is me. I'm anticipating it going down because there is a path through there, but it's going to be extremely high resistance path. So let's see what happens. So let's switch back over to the meter. So here's VB. VB stays pretty dang close to the same, right? Okay. Here's VE. So it went what? How can we have, so it actually went up. I should have known that. But look, on the base we got 5.1. Now my meter's backwards. I hope y'all understand that. Let me get my thing switched back over. Okay, so here's VB. Oh, VB went down. Let's see what VE is going to do. Let me check my supply voltage. My supply voltage is still the same. Okay. This guy right here went down. It's acting like a common emitter. And of course, this guy here is still dropping about 0.6 of a volt. This is VE. This is VB. Wait a second, guys. Why did this go down right here? I hadn't opened up the resistor. Okay, so here's VB. Okay, here's VE. So this guy right here is going to, for this amplifier, is going to be hard to troubleshoot. What's this? So what was it supposed to be? VE, excuse me. What was VE supposed to be? $4.1. And what was VB supposed to be? Yeah, VB is supposed to be 4.8, so it went up. Of course, why did it go up? Because we lost that 500 ohm resistor over there, right? Understand that? But we lost that 1K resistor over there. So we calculated if we use 33K and so if we take 39K and divide it by 52K and multiply that by 10, it came up to give us 5.4 volts. So this is almost perfect now, right? Y'all understand that? Yes or no? So why did it go up? Well, it went up because we don't have a parallel resistor out there anymore. That emitter resistor is not affecting the resistance. Now, normally we ignore it, but it don't change it that much right here, but it actually went up a little bit. This is the guy that threw me off right here. So it actually went up, right? Is a transistor in saturation or is a transistor in cutoff? Huh? It's in cutoff. Huh? This is VE. Let's go and see. And that's what I was telling you. I was saying this guy here is going to be strange. Y'all remember you telling y'all that? So there's voltage collector to emitter. So this guy looks like it's operating. Let's put an AC signal into it and see what it looks like. Huh? Yeah, it did go down, but it's still within our computations. I mean, it's still within what we would expect when we computed the circuit, right? Of course, we should. So here's the base. This might be a little problem. Here's the base. I lost my power supply for some reason, or I lost my meter lead. Okay. So here's the base. It's 5.4 volts. Okay. Now, what should we, if we measure this on the base, what should we expect on the emitter? .4, we should expect 4.7, right? So this is a problem right here. You'll see that? Yeah. So we can see the transistor's not turned on. The transistor we got 3.8 on the base. We got 5.4 on the base, and we have 5.17 on the emitter. Need something?
No, I'll have classes tonight at 8 o'clock.
Oh, okay.
Thank you.
Thank you, Tom. I guess better safe than sorry. So we know we got a problem right here, right? Y'all understand what I'm saying? So look here. This is what? Okay, that's the base. This is the emitter. What we're going to do is put an AC signal on it and see what the actual AC looks like. Because when I measure this, since I've got this on the emitter and I've got this on the collector, it looks like the transistor's operating in the active region, right? But the problem is that we don't have 0.7 of a volt, or about 0.7. This guy here measured what, about 6.5 between the watt, the base, and the emitter. So we're going to see what type of problem this actually creates. So what I'm going to do is I'm going to bring our AC signal and put it back into it, and we'll look at it with the oscilloscope. So this is my input. Let me get back on here. Here's my input. And There's my output. How much are we getting out? You'll see. What are we getting out? Getting nothing out. What are we putting in? Put 3 volts peak to peak in. So this is where we know we got a problem. So normally what we do when we troubleshoot, especially amplifiers, we start troubleshooting with an oscilloscope if we got one. Right? Start at the what? Output and work back toward the what? Input until we find the signal. And whatever we went through last, kind of like motor controls, whatever we went through last has to be the problem. Then what we do is we get our meter out and we check the bias. If the bias is right, we consider the amplifier okay. But sometimes we have subtle little hints that we've got a problem. And what's the subtle little hint here? We don't have that 6/10 of a volt or 7/10 of a volt drop between the what? The base and the emitter. Now this guy here is definitely bad. It's just up to us to try to figure out what it is. And this is one of them that's a little harder. And why is that? Because it looks pretty good, right? If I was looking at whether it's saturated or whether it's in cutoff, the thing looks like it's in the active region. But there's no base current. So that means RE prime is not dropping hardly any voltage at all because there's no base current through RE prime, right? So that 6/10 of a volt is gone out to whack, or that 7/10 of a volt. So it pretty much well measures almost the same thing. It's not the same, but it measures almost the same thing as the base measures. And that would be the little telltale sign. The other ones are real easy to figure out. But when that emitter resistor opens up, that's a little harder to do. What we're going to do next? The next ones are going to be hard to simulate. Because we need to do what? So we're going to open the collector, but remember when you open the collector, we're not going to measure at the collector anymore. We're going to measure where the collector was supposed to be connected, right? So what we'll do is we'll just come over here and take our transistor and shift the collector one lead over. Oops. Okay, guys, so we have an open collector. So what's going to happen? Collector of the transistor is open. This happens a lot. So our open is inside the transistor. That guy right there is gone. Now, what should we expect with VB? Should VB go up or go down? VB is going to go down. And why is it going to go down is that we just lost beta. So if we lose beta, this guy right here is not seen as 100K anymore. This guy is seen as a 1K. Because beta is IC over something. We just lost what? We lost IC. We lost beta. If we lost beta, this 1K resistor is not seen as a 100K anymore. It is seen as a 1K. So this guy is setting that voltage right there. Instead of that 39K setting it, now we have a 1K setting it. It's the predominant resistor. So we should expect it to go down. Transistor, of course, is going to be cut off, right? You understand that. So we should expect VB to go down. Okay, we should, of course, if VB goes down, this is going to go down. We could probably calculate it. It's going to be really close. So let's switch it back over and see if this is what's going on. Okay. So what I did is just move the transistor, the collector over one. But when we measure, we're not going to measure to the collector. We're going to measure to the resistor that the collector was connected to. Right? No, I didn't open up the collector. I opened the emitter. We're supposed to open the emitter? Okay. Collector first. Okay. My fault. Got carried away with it. Okay, so I got the collector open. Got power turned on. Got my meter common hooked up. Where's my red lead? It's right here in my lap. Okay, so what are we going to measure first? dB. We should expect it to go down. And it did. It went down to 900 millivolts. Let's so 920 millivolts. Because there's a lot of difference between a 1K and a 39K, right? Let's check our power supply. It's still sitting up here at 9.8 volts. It hadn't changed. So this guy here dropped down to 900 millivolts. Emitter is going to go to nothing. Yeah, something don't look right, guys. There we go. It's gone to 260 millivolts. So there's the 7/10, right? 900 millivolts, 260 millivolts. That's almost exactly 7/10 of a volt. Voltage collector to emitter. What should we see? Voltage collector to emitter. Should be pretty close to 10 volts, right? And so here's my collector. Here's my emitter. Transistor's cut off. 9.72 volts. Or 9.7 volts. Looks like we should have. I just now noticed the right column, guys. I'm sorry. We're supposed to put a oscilloscope on here anyway. So, okay, guys, what do we need to do next? Okay, so I got my emitter open. What are we going to anticipate? VB should be about the same. It's probably going to go up because we've lost RE prime, right? So it's going to go up to that 5.38 we saw a while ago, probably. Voltage on the emitter should drop down to pretty dang close to 0, right? Voltage collector to emitter should go up to 9.8 volts, pretty close to it. Is that what we expect? Now you got, normally when you do troubleshooting, so what you do is you anticipate, right? You understand that. But normally, when you notice, this is pretty much the same thing that occurred when we opened up maybe another resistor. So when we opened up R1, we pretty much figured this out, right? You understand? Well, what you're going to find out is that it's going to get you within probably 2 parts. Within 2 parts, you should be able to fix this thing. That makes sense? Within 2 parts. So sometimes we have 2 parts that appear to cause the same situation. Of course, what we would do is we would take out one of them and measure it, see if it's okay with our ohm meter, right? But remember, try not to measure these in circuit. Rule of thumb. If you measure in the circuit and it measures okay, we assume it's what? Okay. If it measures bad, then we isolate it and then measure it again. Y'all understand why? Because if it's in parallel with something, it's going to measure wrong, right? So if it measures good in circuit, we assume it's what? It's good. If it measures bad in circuit, we don't assume it's bad. We isolate it, which means if it's a transistor, we have to pull out at least 1 lead, right? Or maybe 2 leads. If it's a resistor, we have to pull out at least 1 lead. Well, pull out 1 lead and then measure that. Okay, so let's see if we got what we anticipated. So here's the base. We expected it to go up a little bit. Looks like it did, not much, but a little bit, right? We should expect VB to measure pretty dang close to 0. By the way, I got my meter leads reversed, but y'all understand that, right? Here's VB. Oops. Oh, I'm sorry, I'm not. This is interesting. Oh, there we go. This is voltage collector to emitter. Let me move my ground back over. So here's VB. We expect it to be pretty close to 0, and it is, right? This is, I'm sorry, this is VE. We measured VB before. So here's VB. We measured wrong a while ago, guys, because I was using the wrong common. So here's VB. That's exactly what it was before when I forgot what was wrong. Okay. Here's VE. Now, what a lot of people do is they'll come and measure on the emitter, but the emitter is open, right? You understand? So what I'm doing is making sure I measure across the emitter resistor. So here's my emitter resistor right here. And what's it measuring? 0, right? Collector to emitter. Here's my collector. Here's my emitter, where it would be connected. And like I said, most people want to measure to the emitter, but remember the emitter is what? Open. So we have to measure to the resistor the emitter is supposed to be popping, and this is what we expect. So the transistor is definitely cut off, right? I'm making sure I got everything put back together. We're supposed to look at the AC signal. That's what I'm trying to do. Just go back here and redo them. Huh. Oh, okay. There's my meter. There's in and there's out. Something's going on. Can y'all see what I'm concerned with? Now, here's my input. This is my output. They should be what? Oh, duh. I'm still going through the 68K, 6.8K. So here we go. So here's in and out. And they should be on top of each other. Okay. So what's the first thing we did? We opened up what? R1. So here comes R1. R1 is the 33K, right? Wow, guys, I didn't expect that. Oh, okay, there we go. Yep. Okay, there we go. We okay? Here's R2, that's next, right? Didn't expect that. So it doesn't seem to be making any difference, does it? I'll have to think about this guy. It looks like it's R2. If we open up the 39K, that should drive it towards saturation, which means it should clip on one side. We're pretty much well driving it as much as we can. Yeah, so this is overdriving it. I don't have a problem in it right now, but so you can see we're actually putting too much in the amplifier than it can handle. So what I'm doing is raising the input right before it starts saturating down here. And then when I open up R2, the output don't change at all. So I'm going to have to think about that. That's not what I expected. Let's go ahead and go through the rest of the table. What's the next one? R1 shorted. R1 is the the 33K, right? But not only does that cause problems with our output, it also shorts out the input too. Because the input is seeing that resistor, right? Y'all understand what y'all understand? So when our input comes up, then that would make sense. So when our input comes flying in, so that guy right there could really cause some problems. So normally my input comes flying in, and what does it do? Some of it goes that way, some of it goes this way, and then some of it goes through RE prime there. Guys, we just shorted out that resistor right there. And what does the AC signal see the DC supply as? Sees it as a short circuit. Now, we're not going to have problems because this guy here has got 50 ohms worth of impedance to it, but it's going to make it drop way, way, way down, right? So the only thing that's limiting the current would be the XOC there. So not only does this guy affect our output, it also is going to cause problems with whatever's driving this circuit, if that guy right there was short. You understand that? So that looks okay. All right, so what next? So man, look at that. Let me make sure I'm shutting the right one. Yeah, so that could cause all kinds of problems. What's next? RE open. So let's open up RE. And we did this before. This is one of them that we did. The output goes to what? Yeah, 0. By the way, the output don't actually go to 0. Let me show y'all. that. Now we can't see it. Normally in AC, if the frequency is high enough, AC will couple through an open. So it's very seldom do you actually see 0 on the oscilloscope when you're dealing with audio signals because it'll couple through opens, right? Now it's going to drop it down quite a bit. Okay, so what's next? Open collector. By the way, I'm doing this with power on. Y'all shouldn't be doing that. So open collector. So this is open collector. Very big problem, right? Let me get it back. We okay? All right. You okay? And then here, this is an open emitter. And it drops to 0. So we're going to do another lab tonight. We're not going to have time to start one if they're going to dismiss class at 8 o'clock. I'll go ahead and give it to you. So what do y'all need to do? This lab will be due next class, right? I need to get y'all lab form. We need to start working on it. When class started. So what time is it now? You need to fill out your lab form. What do you need to do? Number 9, you need to write what you observed in your observation. Number 10, power supply voltage. That's what we need to do. In fact, that's what I did. So let me take all the bugs out of the thing. And let's put some problems into this guy. So now 1 volt per division, 2 volt per divisions. This is 1 volt per division. They're right on top of each other again, right? So what we're going to do is we don't need to look at the input, but so I'm kind of move it out of the way. And we're going to see what effect it has on the output by varying the supply voltage. So I'm going to start varying the supply voltage. Right now I have 10 volts. What do you want to do? Isn't that what it says? The supply voltage? Okay, so here we go. I'm turning the voltage down. So this guy here is not biased quite in the center, so we should see it start clipping. Since this is the emitter, we run out of voltage down here, this would be when we're cut off. If we run out of voltage up here, this would be when it's saturated, right? So here I'm going to start lowering the voltage. So we should expect it to cut off first, right? And how do we know it's cut off? Can you see what's happening? So notice. But this looked very similar to one of our problems when we had a bad part. Of course, when you troubleshoot, what's one of the first things you do? What's the first step we do? First of all, to troubleshoot, you got to understand how the thing's supposed to operate when it operates right. And if you don't understand how a system operates, then you can't do what? You can't troubleshoot. First thing in troubleshooting is you always verify that the problem actually exists. Y'all understand that? I can't tell you how many things I fixed in my career when there wasn't anything wrong. It's just that the person that was operating it didn't know how to operate. And the next thing you do is do what? Yeah, verify your power supply. Verify the problem, right? If the problem does exist, what are you going to do? Check power. So we would have got this fixed just like that. We expected it to measure 10 volts. It measures 5 volts. We would move into troubleshooting our wall, our power supply. An amplifier does not, all it does is control current, right? It is not providing the power. Where does the power come from? It comes from a supply we call the power supply. All it does is manipulate the power. If we don't have enough power available from the power supply, then your amplifiers can't do what they're supposed to do, right? Look things over. Visual inspection usually is the second one. If you got a problem, you look things over. Measure voltage. Then you start troubleshooting. If the voltage is okay, Normally on amplifiers, we troubleshoot from the output back toward the watt, back toward the input. Same thing true on motor controls. When you get into motor controls, you start troubleshooting. You start at the load and then move back toward the source, and you're looking for your voltage. You're looking for your signals. When you find your signals, it's what you just went through, right? What you just went through has to be the problem. Are we okay? So I think that's all of them. I just got to figure out what's going on with that other one. Let me give you out this common collector. I know, I ran off the one on the power amps, and we'll probably use this one instead of the one that's in your bill. Did I give it out to you already? Okay, there's nothing. Why I want you to take this one is that it's got the circuit solved for you. It's got all the math. These guys here are a little harder to figure out. Supposed to be 5 there. Oh, I'm sorry, it's supposed to be 4 there. Y'all got it? Huh? Oh, y'all got, everybody got one? Somebody got 2? If you look at the second to last page, that's the circuit. So it's actually a 2-stage amplifier. And let's look at it real quick before y'all cut out. So I'll bring up the lab. What homework did we do? Oh, y'all supposed to? What was I supposed to do? Oh, notes, yeah. Duh. Yeah, I gotta check that, guys. I really do.
We were wondering how long it's been taking to realize that.
You wouldn't believe what we've been through, but that's still no excuse. Wait a second. Let me show y'all this first. Handout, let's see, Handout Labs. So this is not, you got this in your book, but what I wanted to give this out to you is to show y'all, this is actually a 2-stage amplifier. And we'll probably hook up something to this guy. This is a pretty good amplifier. Nope, that's the same one. Push-pull, right here. So we called it, this guy has several names, a push-pull amplifier, because we have 2 transistors that are basically pushing and pulling against each other, right? So when this one cuts on, this one starts cutting off, and this one starts cutting on, this one right here starts cutting off, you know. And this is the math. So basically what you do is you start with 0. Ultimate goal is to get this right here at 0 volts AC, or 0 volts. We want this guy to be biased at 0 volts because we want them to be Class B amplifiers, right? What's a Class B amplifier? 180 degrees. So what we want these things to do is I want exactly 7/10 of a volt right here and a 7/10 of a volt right there. And if you took, so this will be a positive 7/10, this will be a negative 7/10, which would set this guy right here at 0 volts. And so what you do is you start calculating from here. So you'd come up here and say, okay, this would be positive 7/10. You calculate that voltage drop across that, so you take, -9 or +9. That's a plus up there, by the way. You subtract 7/10 of a volt for it, that would give you that current. Once you get that current, you'd calculate the current. You'd know this because this is a series circuit. You'd use that to calculate the voltage drop across the emitter resistor. We can't calculate the voltage drop across the transistor because it's a dynamic device, right? So we calculate, we know that if this was adjusted to 0, this right here would be +7. I know the size of that resistor. I know this is +0.7. There's 9 volts right there. That guy's going to be dropping 8.3 volts. I know the size of that resistor. I'd calculate the current. It's 10K, right? You understand that. This is a series circuit, so I know this resistor right here is going to be dropping whatever that current is times that. Then we can figure out what this is going to drop, which should be the same as that, by the way. We take this back to the base, and this would give us our voltage right there, and that's what that pot. So most of these things you're going to see a pot because we got to balance this out. So what would we do? How would we adjust this resistor? I'd put my DC meter right here, and I'd adjust this sucker until I got how many volts? How many volts right there? What did I say we need right here? The 0 volts. So that's most of these amplifiers like this. You have to adjust them. So that's what this guy is right here for. What we would do is we would come over here before we started even working on it. I would come over here and I would put my meter right there, and I would adjust this resistor to this right here measured what? 0 volts. This guy we put 8. We come in. This is a what type of amplifier is this? Common. What are we inputting on? What are we inputting on? The base. What are we outputting on? Collector. So this has to be a common. Yeah. You look at what you input on, you look at what you output on, and the other lead is common. Right? You understand that? It's not common to the AC, to the DC, it's common to the ACC. Right? So this is a common emitter. What's the advantage of a common emitter? Get voltage gain. Every one of them gives us power gain. We get a voltage gain and we get a current gain on this thing. So what do we need a voltage gain? What are these guys right here? We're inputting on the base, outputting on the emitter. So these are what? Common collector. They're biased class B. What's the advantage of class B over this guy right here is class A. This guy, these two guys here are class B. What's the advantage of class B over class A? Well, it's a good test question, right? So we already have class. What is class A? Class A is 360 degrees. The output looks like the input. What's the disadvantage of class A? Well, class A have to be biased on. They're sitting there conducting current when you don't even have an input signal on. So they're about 25% efficient. What's the advantage of class B? They're not biased on. They're biased close to on, but they're not on. They're actually off. The input signal turns them on. So if they're not biased on, that means they're very, very efficient. About 75% efficient. So if we're going to get a lot of current drive, we're not going to use class A's. We're going to use class B's, right? This is actually an AB amplifier because if I put an oscilloscope right there, this sucker's going to look like a class A. But it's not. It says that this is going to give us the positive. This guy here is going to give us what? The negative. 75% efficient. So what do you think is driving your stereo speakers out there? Class A's? AB's. AB's. We called it an AB. Why do we call it an AB? Because it generates a Class A output, but it's 75% efficient. Class C's, we use those in RF a lot, but we don't use them in power circuit. Well, we use them in switches. We use a lot of Class C's as switches. We'll oversaturate them, right? All right, guys. So y'all need to bring me y'all's work. Let me see y'all's notes.
That's Dick.
What was it?
That was the homework you read for us as well.
Oh, I'll have to look at this. I'll get that back to you. Okay. Y'all got any questions on that, by the way? I didn't ask y'all, did y'all have that? FPTs? Was the lecture okay? Did it turn out okay? That's good. Any Yeah, I think I told y'all to submit questions. Did I tell y'all to submit
Yeah.
questions? I didn't get any email from y'all. Okay. Do y'all do this worksheet right here? This one right here?
Yeah.
Where's the other circle? Let me check this when we come back. Y'all remind me. Yeah, the worksheet. Wasn't there 2 circuits on there? Or is this one?
Yeah, it's just one that you gave 3 type of.
Okay, guys, y'all be safe.